This is our second of 5 mentor lectures in the mentor lecture series. Today we have a special guest, Eric Stevens from the National Weather Service. Eric is a Science and Operations Officer with the National Weather Service, stationed in Fairbanks, Nome, and Anchorage, Alaska, as well as Marquette, Michigan. Eric had a degree from Grinnell College in Grinnell, Iowa in 1990. It was a Bachelor's of Arts. He's also had degrees from Colorado State University at Fort Collins in 1994, a Master's in Science. His activities that he's been involved with include frequent participation in the Geophysical Institute Science and Math Enrichment Experience. He's also been involved with science camps for middle school students from rural Alaska villages and participation in UAS Outdoor Days, a program that brings middle school students from local Fairbanks schools to UAF to participate in a variety of hands-on activities. So we're going to commence right now with Eric. He's going to be talking about how to conduct an experiment.
How's it going? My name's Eric. I'm glad to be here, and I hope this all works out. Thanks for tuning in. Okay, we're going to gab until about 2:30.
Yeah.
Is that right? First experiment, we'll be setting a watch. Oh, can't do it. Well, you'll have to tell me when it's 2:30. Hello there. This is lecture number 2, and we're going to get started here. Today's lecture, lesson 2. I've got this here, lesson plan. It says conducting an experiment. First thing we need to decide is why conduct an experiment. The most important answer there is because your teacher told you to. Actually, there are even more reasons to conduct an experiment than just that. You can conduct an experiment to answer a question or to investigate whether something you've heard is really true or not. You can test it out with an experiment. This is a casual way of just describing the scientific process, which is an endless loop, possibly, of making a statement, an assertion, or the big fancy word is hypothesis, about how the world works, and then you test it out. You see if it really does work that way by you testing it with an experiment. You do this in the world of science, but it also happens in everyday life, too. Hey, cool. Now I can see me, too. How's it going? Okay. Well, I gotta get my notes here. I did say the scientific process involves a loop between making an assertion or a hypothesis and then testing it out with an experiment. This can happen in the real world, and to exemplify this, to give an illustration of this, we're going to come up with, this is all just a big story here. This is not real, but it will serve to illustrate the point. Let's say that Hal here, who is now coming into camera, good-looking young guy, he could be, instead of up here in Alaska, he could be a high-powered corporate lawyer in Chicago. It's possible. Consider that. I mean, I can see you in a courtroom saying, and Your Honor, guilty. You know,
guilty as charged.
Exactly. But you know, high-powered lawyers who work in skyscrapers in Chicago, they gotta look sharp. And Hal's, he's starting out young. Maybe he doesn't have a lot of money, so he's only got one suit. He's got one shirt. You have a sport coat, tie. He's only got one of them. He looks great, but every day after work, he goes home to his apartment there in the skyscraper, and he has to wash his clothes. And then, puts them through the washer, puts them through the dryer. And then he has to get the ironing board out of the closet, iron his clothes, and iron his one shirt, and then he puts the ironing board away. And he thinks to himself, because Hal's a sharp guy, he thinks, this is a big waste of time with this ironing board. Every night I take the ironing board out of the closet, set it up, iron my clothes, put the ironing board back. I know, I have an idea. He comes up with a hypothesis. Hal's big idea is, I could save time. I wouldn't have to put this ironing board up and put it away if I would just put on my shirt, wrinkly, and then I'd iron it on myself. This is a great idea. I'll save 5 minutes every day by doing this. So Hal gives it a try one morning. He puts on his wrinkly shirt, gets out his iron, which, let's pretend this is an iron right here. Now don't do this at home. Okay, so Hal's got his shirt on, takes his iron, goes like this. Okay, now you scream. Okay.
Burning!
This is hot. We've learned something. Hal has a 2nd-degree burn over his belly button, has to go to the hospital and spends hours there. He tried to save 5 minutes, and actually, he wound up losing hours of time. This is from the Department of Bright Ideas. In life and in science, sometimes we come up with something that sounds good to yourself when it's just up in your head. In our heads, we think of something, we get an idea, and we don't really know the practical limitations. We think about how good the idea is, but we haven't really tried it out yet, so it seems perfect to us up in our imagination. But when you try it out in the real world, maybe there are unintended consequences. Maybe there are problems we hadn't considered when we first came up with the idea. That's why you do an experiment. You have an idea in science. You come up with, again, that word hypothesis. You come up with a theory or just a statement about how you think something works in the world. Then you test it out with an experiment. You do a real live experiment there to verify whether you're right or not. In our case here, we all got this lesson plan here, and on the second page, at least my second page, we've got this description of our experiment involving a coin. We have here a genuine American quarter from 1984, very good year for quarters. And we will flip the coin to test out our hypothesis. And, okay, I'm checking my notes here to make sure I didn't forget anything. Okay, are you doing all right over there?
Yeah, doing great.
You recovered from your burn?
Still a little
good deal. Well, in our case here, the hypothesis was, since you flip a coin, it's either going to come up heads or tails. Those are the only two options. So, since you have a 50% chance of getting heads, a 50% chance of getting a tail, that means if you flip this coin 10 times, since half the time it's heads and half the time it's tails, that means that after 10 flips, you'll have 5 of each. You'll have 5 heads and 5 tails. End of story. Now, you might think, we're so right with that, we don't even need to test it out. But you really should. This is where science is nice and self-correcting, at least ideally. We'll test it out in the real world and see what happens. Again, just like the idea that I'll save time by ironing my clothes after I put them on, that really didn't turn out to be true once you put it into actual practice. We come up with an idea about coin flipping and how it should work out by flipping the coin. But is it really going to work out that way? Well, the only way to find out is to try it with our genuine vintage 1984 quarter here. First of all, whenever you do an experiment, you've got to keep a couple things in mind. You've got to have the right kind of hardware. This is a pretty simple experiment. We have a quarter. We have a table. We had the laser level out earlier. This table is absolutely flat. We have a pad of paper, and we have a pen, and we can record our results. And now, we will produce the experiment that you have already done, or some of you have already done. We're going to flip this coin 10 times and record our results. In fact, we're going to do this a couple times. This will only take a few minutes. Now, would you please flip away for Series 1? Flip number 1.
Here we go.
Here it is.
Flip number 1 is tails.
Tails. Number 2.
Heads.
Heads. Number 3.
That was a high one.
Heads. Number 4. Heads. Oh, wow, lots of heads. Number 5. Tails. Number 6. Tails. Ooh, 3 and 3 so far. It's working out great. Heads. Tails.
4 and 4.
Oh, boy.
2 more.
Tails.
And the last one
is tails. Wait, did you say that? That was tails.
Yeah.
You guys keeping track out there in TV land? Wait a minute now. We're going to count these. Heads. We have 4 heads and 6 tails. That's not right. Wait a minute.
Supposed to be
Our hypothesis is airtight. If you flip a coin, you either get heads or tails. 50% chance. And here, we got 6 tails and 4 heads. Let's do it again, Hal. All right, we're going to do it again. All is right with the universe. Heads. Flip number 1. Number 2, tails. Hal's a very good coin flipper.
It could be like an NFL.
Tails. Yeah. Where'd you
It could be
go
like a
up?
sporting
Anyway.
event.
Heads.
Okay.
Next. Tails. Okay. Flip number 6. Heads. Okay, 3 of each. This is working good. Heads for 7. And flip again. Heads again. Okay, 2 more to go. Tails. And tails. Okay, so for heads, we got 1, 2, 3, 4, 5 heads. And tails, 1, 2, 3, 4, 5 tails. Well, now that's what we expected. Okay, so welcome to the scientific process, everybody. We had an idea. We had our hypothesis that the coin should flip 10 times, you get 5 heads, 5 tails. We went and did it right here, just like a lot of you have already done. And you know what? I bet our results are a lot like yours. We did it twice here. One time it did come up 5 heads and 5 tails, but this other time it came up 4 heads and 6 tails, not 5 and 5. What's going on? Well, this is often what happens in science. You start out with a good idea, you take an experiment, and it doesn't turn out the way you wanted. Why didn't it turn out the way you wanted? There are a few possibilities here. First of all, there might be something wrong with your original idea. In the case of Hal with the iron, and he never really did this on his own. I happen to know that Hal was not a high-powered corporate lawyer in Chicago. It was Seattle, right?
I think I actually did try that
Yeah,
one.
there you go. And in that case, Hal discovered that there was a problem. It was actually his original idea was flawed, that I'll save time by ironing the clothes once I put them on myself. It had unintended problems. His original idea, his hypothesis, had a flaw in it that was revealed by the experiment. So when an experiment doesn't work out with your plans, why is that? Could be something wrong with the original plan, the original hypothesis, or maybe there's something wrong with your experiment. In this case, we need to be sure that we're not using like a two-headed quarter or something. And we can verify that this is tails and heads and tails. It's a two-sided coin, just like they all should be. We don't see any obvious source of error in the process of our experiment. Whenever you do an experiment, though, you always got to keep an eagle eye out for things like that. If there's a source of error in your experiment, that could pollute your results, and you want to keep away from that. Now, we can't tell you here every possible thing that could get in the way of your experiment, but you want to just, use your head. And in this case, if Hal was only flipping the coin like this, that would not be a good way to flip a coin. You need to do your experiment in a way that's meaningful and valid. Okay. Well, in our case here, I don't see any flaw in the way we did the experiment. We took good notes, we wrote down everything that happened, flipped the coin, but we don't have an answer that backs up our original hypothesis. So, I think what we're going to do is we have to modify our original hypothesis. We got to come up with a new hypothesis. Well, whenever you do an experiment, you might learn something that can help you change your original idea. Actually, in science, the process of doing experiments and learning from them and coming up with new ideas never really ends, because you can kind of get in a loop where you learn one thing in your experiment and that helps you change your idea. So you test out that new idea with a new experiment. Well, that experiment might teach you something new, and it goes on and on and on. Science is not something that sits on a shelf and gets dusty. It's always improving itself, at least ideally, through this process of experiments and new ideas. Here we had an idea, we tested it with the quarter experiment, and now we got to come up with a new idea to incorporate our results from the experiment. Our old hypothesis was you will get 5 heads and 5 tails because of the 50-50 nature of the coin. Maybe our new hypothesis should be this, that when you flip a coin one time, you'll get either a head or a tail. You flip a coin 10 times, and you'll have a combination of heads and tails that could actually be quite varied. It's possible you could have 10 heads. You could have 10 tails. You could have 1 head and 9 tails. You could have 2 heads and 8 tails, 3 heads and 7 tails, all along. There's actually 11 combinations there, all the way from 10 heads over to 10 tails. Those are all real things that can happen. And I ran this out on a piece of paper here. These combinations are, it's right here. You can find out more information about this on the internet. The internet is great. If you do a search for binomial expressions or just coin flipping experiments, you'll find out that if you flip a coin 10 times, you actually only get 5 of each, 5 heads and 5 tails, like 1 out of every 4 times. Those other 3 out of 4 times you do the 10 flip experiment, you're going to get something else. Like what we got here, we got 6 tails and 4 heads. That can happen pretty frequently. And that's good. So we come up with our new hypothesis. Maybe a new and improved hypothesis could be, I think I wrote this down in here somewhere. Yeah. So if you flip a coin if you flip it 10 times, you'll get any one of a possible 11 combinations of heads and tails. It'll all add up to 10 flips, but we can't say beforehand exactly it'll be 5 and 5. It could be anything from 0 and 10 to 10 and 0, and in the middle would be 5 and 5. It'd be more likely to get 5 and 5 than 0 and 10, but where exactly our 10 flips is going to put us, we can't really say ahead of time. So, it turns out things are a little more complicated than we thought. We had an idea at the beginning, we tested it out, and our test reveals that we need to change our idea if we want the idea to be right. And science is kind of fun because this is a place where it's not entirely a loss to be wrong. When you're wrong, you actually have an opportunity to improve yourself. You found out you were wrong in your experiment. The good thing to do now is to take these results and go, why was I wrong? I know, I'll try and improve my idea. Then you test that idea out, and that idea, the new idea, ideally is a stronger idea and will be closer to the truth. And again, we just do this in everyday life. It's called learning from experience, live and learn. If you, let's say Hal's sick of ironing himself in Chicago, so he goes to Los Angeles, where I've never been to Los Angeles. I've heard, though, that you can't hardly get anywhere there in a car because it's so crowded, so much traffic on the roads. Hal needs to be at work at 8 o'clock in the morning. But he discovers that if he leaves his house at 7:30, he'll be late. So he says, well, I can't leave at 7:30. I'll try a new thing. He's going to leave at 7:25. He's still late. He says, well, I got to get to work at 8, and I thought if I left at 7:25, I'd be there at 8. But no, it didn't work out. And by trial and error, Hal finally, when did you have to leave your house to get there?
Leave at 4:30.
4:30 a.m., and he only had to go 4 blocks. But that's
Really
that's how bad traffic is in Los Angeles. But with Hal, in real life, this is a process of learning from experience, trial and error, coming up with an idea, and then testing it out in the real world. You have a hypothesis, and you do an experiment. In science, we do this, and you take notes on paper, and it's all very formal, and you get graded on it. But in real life, we do this all the time anyway. It's just live and learn. You learn by doing, and as we get older, as we learn things, we get better at things because we've done them before, and we've learned the hard way where the pitfalls are, where some of the mistakes are. And that's what the scientific process really is. It's a very formal way of just saying you learn by experience. And that's what people do all the time. We all know more now than we did a couple of years ago. Some of us are really old geezers. We ideally know more now than we knew 20 years ago. And that's why when you get older, you hopefully get wiser because you've learned by experience. And there's a couple of words that are in common here. Experiment and experience are almost the same word. And they really come down to the same thing. That's just by observing what happens when you take certain actions in the world, and then you learn from them. And ideally, you improve your performance the next time because you learn from what you did in the past. I think that is the big wrap-up.
That's great.
Hi, this is Bob Youngwell from Gamble. I have a question. How do scientists use models to study the climate?
How do scientists use models to
Yeah, the question from Gamble, that's a great question. How do scientists use models to study the climate? Our modern computer age gives us a real advantage that we didn't have even just 10 or 20 years ago, and that is computers are so powerful that you can write a computer simulation of the atmosphere of the whole planet, and then you can tell this computer to pretend that hundreds of years are going by, and then you wonder, well, how do things change with the weather? Scientists use computer models to study the atmosphere and how the climate will change into the future by maybe playing around with the model a little bit. One of the big issues right now with the possibility of climate change is what happens to the atmosphere when people put more carbon dioxide into the atmosphere. A scientist may write a computer model of the atmosphere and then say, well, I'm going to change one thing. I know this model works pretty good for today, but what if I doubled the amount of carbon dioxide in the air? How would that change things? And then you tell the computer model to go, and it crunches away and comes up with an answer that, the atmosphere will be different in this respect because of what you did here with the carbon dioxide. So that's the really good thing about computer models. One thing I should say, though, about what I understand of computer models is, there's this old saying that someone who has one watch knows what time it is, but someone who has 2 watches is never sure. And there's a lot of different computer models out there. And not all the computer models agree with each other. There's a spread of solutions. And that doesn't mean that any one of them is totally wrong or maybe one is totally right. But you need to remember that there's still a lot to be learned about this. And one thing, the climate forecasting is still somewhat uncertain because there's a lot of noise in what the computer models can tell us. we have some other questions here too. And I should also point out that with regard to computer models, they're good for telling us what might happen 50 years from now, or 100 years from now, or 1,000 years from now in modeling climate. But where I work in the Weather Service, we're concerned with what will happen in the next 2 hours or the next 2 days. For instance, up at Barrow, the fog is down hard, and Alaska Airlines needs to land a flight at the airport in Barrow. But the fog is so low, the fog is so thick that they can't land the airplane. When will the fog move out so they can land the plane? We need to give them a forecast of that kind of information, and we use computer models that focus much closer in time. So computer models are really helpful in the immediate time, like next 2 hours or next 2 days, as well as a further out time for climate study in the next 200 years.
We have another question here, a question from Unoclete. Eric, the question is, do you use the scientific method each day?
Yes, we do, in the sense of you learn from experience. In Alaska, this is a little tougher to do than it is down in the lower 48 part of the United States. And that's why it's so important, some of the weather hardware that you've got at your schools that Hal has been setting up. Because to learn from experience, you have to know how your experience went. When in our office, we write weather forecasts for the northern 2/3 of Alaska. Everything from the Yukon Delta on north along the west coast of the state, all of the interior of the state, and the Arctic coast. And in some parts of Alaska, there's not a lot of ground truth data. We may say that along the Brooks Range between the Dalton Highway and Arctic Village, there'll be 2 inches of snow tonight. But there's nobody there telling us whether that happens or not. So the next day we come to work and we wonder, well, were we right? Did it actually snow 2 inches? And unless maybe some bush pilot was out there or someone happened to be there who tells us what happens, we won't know if we were right or not. And when you don't learn how you did, it's hard to learn from experience. But at other places, we do have information. At Kotzebue, the airport at Kotzebue has great weather sensing gear, and so we learn about what's happening in Kotzebue. We have observations that come in every hour, or even more frequently than every hour, sometimes when the weather is changing. And that truth, those observations of truth, help us learn about what we are doing. And this helps weather forecasts get better. You know, Mother Nature is always going to be able to throw a curveball at us, and we're never going to be 100% right. But today, a forecast that we give for, say, what weather will be like in 3 days from now is as accurate as a forecast for 1 day from now used to be, say, 10 or 20 years ago. So we're learning from experience, and we're getting a little bit better. To learn from experience, though, you have to know how you do. In our experiment here, imagine if you flip your coin 10 times, but you couldn't see what the coin did. You didn't know if it was a heads or tail. That would make it hard to learn anything from the experiment. So you have to be able to observe what happens. And in the weather business, we have to do that all the time. Sometimes in Alaska, though, there are holes in the data. And that's why it's good for the schools to be getting some weather gear. That's very important information.
Yeah. We have another question from someone named Mia. She asks, give us an example of an experiment that the National Weather Service might be conducting currently.
Might be conducting currently. Oh,
yeah.
Boy. Well,
good question.
I'll say this. In our office, right now we've got an assignment that all of our forecasters have to do in the next couple of weeks. And that is, they need to write down, they have to do a paper. They have to do a homework assignment. They just have to write a quick couple of page paper about something that they have learned by their experiences that maybe the computer models don't do very well, or something that someone who came to work for the first day ever, some brand new person, might not know. We want people to document, to write down what they have learned, so that when these people, if they retire or if they move away, that they don't take all of their knowledge with them, because so much of what the science of weather forecasting understands is kept up in here, and we want to have that written down. So in that respect, we are trying to have people write down the results of their own experiments. When people have learned through years of forecasting that in this kind of weather pattern, Fort Yukon gets a lot of snow, or in this kind of weather pattern, Unalakleet will not get a blizzard, but Nome will get a blizzard when the high pressure is here and the low pressure is here. We need people to write that down so that the person who comes after them doesn't have to learn it all the hard way themselves. They can see further because they stand on the shoulders of the people who came before them.
We have a question here from Shishmarev. The question is it hard to study specific events in weather and climate. For example, conditions have to be right to study the specific thing. Is it hard to do that, or do you tend to study trends?
Wow.
What a question.
Hal, you didn't say these were going to be tough, good questions like that. Well, with regard to specific events, sometimes it can be tough to study a certain event. I'll give you an example. There are some clouds that produce snow that might affect Shishmaref, or there was an event at Nome and Teller 5 years ago where there was a certain kind of cloud, a cumulus cloud, that was dumping heavy snow showers. And we could see those clouds on the satellite picture only because there were no higher clouds above. You know, the weather satellite is way high in outer space, and it looks down on the ground. And if the weather that's causing the snow is down at the bottom of the atmosphere, but then there were a higher layer of clouds in the way, the satellite up here couldn't see the important stuff going on down there. So in that respect, sometimes it's tough to study one given event because the circumstances might be unique. Maybe there are higher obscuring clouds that are getting in the way of the important clouds that you want the weather satellite to see. But you asked about trends, and that's an important thing too. Now, that begins to get us into the issue of maybe in the longer term into climate change. Is something changing over the course of decades or centuries? But even within one given year, it's important to keep an eye on the trends too. I hope I'm answering your question right here. But in this part of the planet, we're not quite on the North Pole. We're still, we're not quite at the very top of the planet. We're getting down a little bit, and that's important because right at the top of the planet, the weather is different up there. Here in our part of the planet, the weather tends to come in trends where you can have, maybe in the wintertime here, there's a cold snap where for a whole week, it seems like every day the weather is the same. It's cold and there aren't many clouds and the wind is always out of the same direction. But then something will change and the weather will be a certain way for maybe a trend of 3 or 4 days. The weather's warmer and maybe a little bit wetter. And then it will go back. So it's important to keep a track of where you've been these last couple days because that may indicate a trend of what today and tomorrow will be like. And in the weather forecasting business, one of the most important things to keep in mind is that you'll never be able to forecast where you're going until you know where you are now and you know where you've been. And in that sense, that is the studying of a trend over time. We know where we were 2 days ago. We know what the weather was yesterday. We know what the weather is today. This will help us forecast for tomorrow. So that's an example of using trends.
We have a question here from Mary, who's in 2nd grade. She asks, can experiments be dangerous?
Well, they sure can. You need to use whatever precaution your teachers tell you to when you're doing an experiment. With our experiment here, flipping a quarter is pretty safe. But if you get into high school, maybe you might be in a chemistry class, say, which would involve mixing some liquids. And when I was in chemistry class in high school, we had to wear these nerdy chemistry goggles, these big, thick plastic things. And why is that? That's because we don't want maybe you're mixing chemicals that are dangerous, or perhaps they could be a little bit of an acid, and you don't want to spill that in your eyes. So you need to wear the clothing that's appropriate for your experiment. And I suppose you could say that in our own lifetimes here, something like the space shuttle disintegrating in 2003 when it was coming in for a landing down in Florida, and over Texas it broke up in the atmosphere, that would be an example of a dangerous experiment. We are still just learning how to travel into outer space, and it can be dangerous up there. You need to be as careful as possible. In a school environment, always follow the instructions that your teachers give you and what the textbook may have for how to handle chemicals safely, for example, in chemistry class.
There's a question from Euclid, Eric. The question is, how does weather data get into the computer model?
Good example would be what we're doing right now. We are communicating over a long distance by electronics, by the miracle of the internet and communications by satellite and such. Weather data right now can travel great distances very quickly, just like on a telephone. You could talk to someone who was living in Texas maybe, and your voice will go down there. And right now we're even video conferencing. We're all the way over here in Fairbanks, and schools all along the western coast of Alaska in the Bering Strait, we're all linked together with the telecommunications network. So the same infrastructure that allows us to communicate can get weather data all around. And in the United States here, the computer models that we use in the Weather Service, they are run on big, huge computers that still take up entire rooms all in Washington, D.C. That's where they have the big building with the supercomputers, and they run the computer model. So all the data has to go to Washington, D.C., and then the computer model can grab a hold of that data and go, okay, I understand this, and then it will make its forecast.
We have another question here, and this question says, what experiments are you currently conducting for the GI? And I think the students are aware that there's a Geophysical Institute that we're involved with some of the curriculums like Aurora Alive and this new grant, Arctic Climate Modeling Program. Maybe it would be good to touch base on the Geophysical Institute and how these different research places work together.
Right. Okay, well, there's one thing that's very exciting that we're working on right now. I just said that the computer models are run in Washington, D.C., but the university here has a supercomputing center, and we're just beginning a project now where we are going to run a computer model specifically for Alaska, specifically for the northern two-thirds of Alaska. And the computer model will be, since it's only going to focus on a smaller part of the world, it's only going to be worried about us here in Alaska, the computer model will be able to see much smaller weather features. And we're hoping, we're going to learn by experiment, by trial and error, we're hoping that this computer model can be taught to recognize some of the weather in Alaska that is caused by all of the topography. In Alaska, we have huge mountain ranges and broad river valleys and a long coastline that is covered, then the ocean is covered by ice, and then the ice retreats. All of these things down here at the ground, the mountains and the rivers and the ice and the coastline, that all affects the weather. And some of the big computer models that are run back in Washington, D.C., they don't understand those subtle features of our Alaska weather here that are driven by the topography, by the mountains and by the ocean. So we're hoping that our new computer model that we're developing here will be able to see some of these things. And we're going to learn by trial and error. We've got a couple of test scenarios that we're going to be running on this computer model to see how good it is. One example is not from the coast of Alaska where you are, but it's in the interior here at Delta Junction. It's a very windy place at Delta. And the reason it's windy is because the wind flows through narrow mountain valleys. And we're hoping this new computer model will be able to recognize that and see it. This may teach us something, and maybe we've got the wrong idea. Maybe the computer model will tell us something that we didn't know, and we'll have to change our hypothesis. It should be an exciting time, and it's a great example of what the university is able to do.
Has the climate changed?
Has the climate changed? I guess one thing we have to concentrate first on is what time scale are we talking about? The planet Earth has gone through a lot of climate changes in its history. The best scientific estimate is that the planet is 4.5 billion years old, and the weather that we see around us now, the climate we have now, has only been with us for just this last few, tens of millions, hundreds of millions of years, which actually isn't that long when you consider the entire lifespan of the Earth. Most of the time the Earth has been here, the atmosphere would have been poisonous for our kind of life. And so, in that sense, the climate has changed radically as the Earth has aged over 4.5 billion years. And then even on a more narrow time scale, over the last several tens of thousands or hundreds of thousands of years, the best estimate is that we've been in a cycle of ice ages and then retreats from ice age, back and forth, ice advancing and retreating. And there's a lot of climate change with that. And I think where you were going, though, with your question is right now, are we in a period of accelerated climate change that may be due to human activity? And that is a great question. And I want to know the answer to that myself, because Alaska, I'll get back to these models about the climate, the computer simulations of the atmosphere. I said earlier that many of them have different kinds of solutions, and they do have different kinds of solutions. But a lot of the climate models do say that whatever climate change will occur could be more noticeable up here in the higher latitudes. Up toward the North Pole, that would mean Alaska and northern Russia and northern Europe and Canada. The manifestation, the amount of change that could occur would be more noticeable up here than it would be down, say, in the tropics. And so we really need to pay attention to that. I'll have to say, I know just a little bit about the processes of climate change. It's very complicated. There are many feedbacks. For instance, if it gets warmer, does that make more clouds? And then if there are more clouds, does that reflect sunlight back out to space, which makes the planet colder? There are the positive and negative feedbacks that are intertwined, many, many variables. And I'm going to have to punt a little bit on the climate change one for making a specific forecast. I'd probably want to pass that one off to faculty at UAF who study climate more. As I mentioned earlier, at the Weather Service where I work, our job is to protect lives and property by issuing weather warnings and forecasts for this next couple of days is what we really focus on. We want to help Alaska Airlines know when they can get a flight into Barrow. Or if a blizzard is coming to Kotzebue and Kivalina and Shishmaref, we want to give you 24 hours or 36 hours of lead time so that you can know not to be traveling when the blizzard comes. And that's what we focus on. So our time scale, we're right here. We want the immediate time. And the issue of global climate change is a longer one. I should also point out, too, that the planet, and this is one thing that makes the question so tough to answer, is that the planet naturally does change. And everyone is concerned about, is climate change due to what we've done? Have we polluted the planet, and have we made something change that wouldn't have changed otherwise? It's tough to know that because the climate does change anyway. There are ocean circulations that turn on and off, but it takes them decades to do this. The ocean is a very big and slow-moving thing. And the ocean can be in a certain phase of circulation for 30 or 40 years, and then it may change and be different for the next 30 or 40 years. That will lead to a change in our weather here in Alaska, but is that caused by our human activities or not? It's a really important issue, though, and we can't just sweep it under the rug. And I think some of the university's work here, there are some good faculty members here at the university who work more on that long-term climate study, and they need to keep doing their work. It's a very important question, especially for us in Alaska.
There's a question from Lloyd in Wales. He asked why you chose your specific field of study.
Oh, because it was fun. I guess I just lucked out in that I was thinking, what would I want to do for a job? And I'd like to, when I was a kid, when I was in middle school and high school, I was one of these nerds who would write little science fiction stories and stuff like that. And I thought, well, maybe I could write stories, but then I thought, there's no money in that. And then I like to play the guitar, so I thought, well, I'll be a rock star. But that's really not practical. But then I also kind of like the weather. I grew up in North Dakota, as I was telling Hal, in eastern North Dakota, where they have blizzards all the time. It's cold and windy. Winter is really something there, and I used to like being in our house during a blizzard out there, and you could hardly see across to the next house. We lived in a really small town there, and the blizzards were really something. I always wondered why that was. And in the summertime, those puffy clouds, they're puffy on top, but they're flat on the bottom. And I thought, why is that? How come they're not flat on top and puffy on the bottom? And I think a lot of kids wonder about the weather because it affects us every day. It's cold out or hot out, and we notice these things. And so I went to college, and I decided to study the thing that I thought might be the most practical for future employment. I thought, well, maybe in the weather business it's easier to get a job than trying to be a rock star guitar player.
Oh, we have two more questions that we're going to ask and have answered here, and we're not going to take any more questions at this point. So we're just going to answer these two that we have. Eric, there's a question from Diomede. The question is, do you ever get to go to villages to do experiments? If so, what kind?
Boy, oh boy. I guess I'll say that I haven't ever been to a village to... Well, maybe I can stretch the answer here to... I've traveled along the Dalton Highway. I haven't gotten off the road system, but here in the interior I've been on the road system to measure the thickness of ice in rivers and lakes, especially when we get up close to breakup. But all through the winter we do this, actually, once a month, but we really try to focus on April 1st or March 31st. Want to measure the thickness of the ice. Why do you want to do that? Because the thickness of ice on rivers and lakes can have an impact on what the spring breakup will be like. It has an impact on the likelihood of ice jam flooding in the spring when the rivers start to break up. And so I guess that's, in a sense, a very long-term experiment where through the entire winter you go out once a month and then you really do a good collection, especially around April 1st. And we've done this for 5 or 6 years now, and we're beginning to accumulate enough data that we can start to make some conclusions based on, we can make a new hypothesis based on the data we've gathered. So I guess we have done experiments, although we haven't gotten to the villages, but we've gotten out in Alaska, at least on the road system. It's so expensive to get an airplane to do this that we just don't have the money for that. But we are learning that there is a relationship between the thickness of ice on the rivers and then the likelihood of ice jam flooding downriver during spring breakup. So that's important to know.
Eric, our last question is from Wales. Rachel would like to know why there seems to be more storms this year than previous years.
Why there seems to be more storms this year? Well, I'll say this. Maybe this gets to the global climate change question again. Every year is different. You know, if we flip this coin 10 times, one time you flip it, you'll get 5 heads and 5 tails. The next time you flip it, you could get 7 heads and 3 tails. The next time you flip it, 6 tails and 4 heads. Every series of 10 flips will be different. Even if you get 5 heads and 5 tails, maybe you'll get all the 5 heads first, and then the 5 tails. So we're still early in the winter season. I'll say, too, that in northern Alaska, the stormier time of the year tends to be the first half, when there's less ice, or the first half of the winter, I should say, when there's less ice on the Bering Sea, because storms are fueled in part by open water in the Bering Sea and in the Chukchi Sea. That open water gives moisture and warmth to the bottom of the atmosphere, but the atmosphere, it's getting to be winter, so the atmosphere is getting colder, and that contrast between hot and cold helps fuel up storms. So this is a good time of year for there to be storms. Every year is different, though. I'd hate to say that one year establishes a trend. I remember the winter of, I think it was 1995 to 1996. It was exactly the opposite of what we would normally expect, when in the November and December, the first half of the winter, it was real quiet weather. And then in February, which is normally a quieter month, it was stormed all the time. And that's just the way it is sometimes. Variability is a natural part of the weather process. And given this year the storm track has been a certain way, you know, at some point, I guess, even in the weather business, if you ask the question why enough times, you'll get back to a point where you just have to say, well, that's the way it is.
I always like to think in terms of the kinetic theory of molecules when I think of gases. Could you maybe explain wind and how you get, massive motions within, within the atmosphere in respect to how the kinetic theory of molecules works? I know it's a little bit of an oddball question, but I always find those things really interesting.
Yeah, well, one thing that sticks out in my head might be the ideal gas law, PV equals nRT, is something that we do need to keep in mind. And maybe one thing where that's applicable even in what we do in the Weather Service, the implications of the ideal gas law are that if you take a piece of air and expand it, it will get cooler, or if you compress it, it will get warmer. And that leads to the consequences of that do include, as you go up in the atmosphere and the pressure gets less, that you have cooling with you. With regard to the motion of the atmosphere, one thing that seemed really interesting to me when I was in college is, and they told me this, and then I guess I proved it. I mean, we all had to do this as an experiment or a homework assignment dealing with the equations, was that air is a fluid just like water is. And the only difference really from a mechanical point of view is that air is compressible and water or fluids basically are not. They are a little bit, but so that's an important thing to keep in mind, that the atmosphere around us circulates like you might see water circulating. And that, when I was introduced to that idea, it helped me visualize how air would flow, and even concepts like, as I was mentioning earlier, there's wind at Delta Junction here in the interior when the wind is funneled by the mountains, much like you could imagine if you poured some water over a 3D topographical relief map of an area, how the water would wriggle through the valleys and such. And in that sense, the air behaves, all the molecules are lining up, and when they get squeezed through a mountain pass, they accelerate because they're still being pushed in by the fluid dynamics, I guess, in the sense that like a liquid would as well, almost like a plumbing theory. And that helps explain why there are accelerations of winds through mountain passes that we see here in the interior. Hope that answers the question there.
Okay, my question is, how would you go about letting your kids create and conduct their own experiments? How would you set that up so that they could go through and come up with their own experiments and conducting them, and ways to test their theories and hypotheses?
Okay. Hey, we can see you now down there. Well, that's a good question there. Hey. Well, I suppose you would want to, first of all, do something age appropriate there. One of the important things to keep in mind in an experiment is to make it fair to kids that it needs to be duplicatable or consistent from kid to kid. We had, in the first physics class I ever took, the teacher came up and on the very first day of the class he says, here's the difference between physics and biology. And he had some kind of a inelastic collision thing where he ran a little car on this air hockey track kind of thing so there was no friction on it. It was suspended on a cushion of air. And then it slammed into another thing, and you could describe the collision process mathematically. It says, that's physics, and we had the equations and all that. And then he had in a little jar, he had a cockroach or some kind of a bug, and he put that on the table, and the bug just wandered around. And he says, and this is biology, and the difference here is that the physics experiment will be reproducible, ideally. If you divide the kids up into groups of 2 and they all take a turn at the little inelastic collisions experiment on the air hockey track, ideally, everything being equal, they should get the same result from the experiment. But if they all had an assignment to let the cockroach out of the jar and see what it did, they could get all kinds of different results that might not be meaningful for anything. Hal and I were wondering what kind of experiment would we want to use for this presentation. And we talked about a number of things. And the considerations we had were it had to be something that was simple enough to do without a lot of fancy hardware. It had to be something safe. We couldn't have the hydrochloric acid uranium experiment. It had to be something that would be appropriate to the age groups. And here we knew that the kids were going to be of all kinds of ages, and we were wondering what best to do with that. And we came up with the coin flipping one. Oh, another one we were concerned about any unintended competitiveness in an experiment. Because at first we were thinking, well, a lot of kids like to play basketball. Maybe we could have an experiment where you shoot 10 free throws and record how many baskets you made. But then we thought, well, maybe, there's some kids who are always good at basketball and other ones aren't very good, and that they would feel bad, or that would introduce extra baggage into the whole experiment that we didn't want. And so we came up with this one. And this experiment, too, has one advantage in that it opens the door to stuff that's really a lot more complicated. It's a pretty simple experiment to get started. But if you go on the internet and do a search on Google for binomial expression or binomial distribution, holy cow, it gets into heavy-duty statistics and symbology that I saw in college and forgot all about. This kind of experiment is scalable to maybe kids in the elementary years would like flipping the coins, and then you get into the high school kids who might be able to work with the statistics more in depth, and all the way up to heavy-duty college work in statistics, I would think.
If we could take a second to ask you a question, as we lectured about experiments, did the children seem interested in this, or did this seem beyond them, or did it seem appropriate for their age level?
I think we're probably always going to be faced with the problem that I'll describe is we have a really large age spectrum here, all the way from like 2nd, 3rd grade all the way to high school. And I think it's really hard to actually hit that whole spectrum at one time. In fact, it might be good to even consider having lectures for different age groups. Our younger kids, they really had almost no way to understand a lot of what was going on. I thought your presentation was absolutely terrific. It really was very wonderful, very well conceived and well presented. But it was really geared towards high school students, and we didn't actually today we only had one high school student here really, and he was really taking it all in, so it was very appropriate for him.
Mm-hmm.
Yeah. At this time during the day from 2 to 3 is my special ed science class, and their level is like grade level 3, and so they have a hard time grasping it. But I think some of them were able to understand what you were saying.
Do you have suggestions for us?
To to what Linda here is saying. Yeah, I think in a second, but I was going to say is that, you know, sometimes it's just good for them to see a scientist.
It is, yeah.
You know, it takes some of the mystery out of it, and I think you did a great job on just being a real person.
Oh, yeah.
And that's good for them to see. It's always, so sometimes they take that away as a very important part of what they experience. But yeah, I think the suggestion is to maybe to do the lectures for different age groups, and that we can actually plan ahead for that in that way. I think might actually work. It might be real helpful.
We'll look into it.
We'll look
Yeah,
into
you know,
that. Thank you very
can we
much.
just jump off the line for a second to see if anybody else has questions, because I actually would like to run by an experiment that we have already done and that we're going to continue doing for a science fair project. How about if we jump off the line for a second and see if somebody else is online and wants to ask a question?
Okay, it seems like there aren't other schools right now, so if you wanted to discuss that with us, I think this would be a great time for that.
We've been doing an experiment in my class that we're actually trying to get ready now for a science fair. In fact, we're going to be automating it so we can do automatic data collection, but up until now we've done it just manually. We're trying to actually model, with a physical model, not a computer model, to model the Sun-Earth interaction in terms of how the Earth stays at a steady state temperature, and then also how it can then change through the factors that create global climate warming. So what we've come up with so far, and it seems to work real nicely, is just a cardboard box. We want to do it cheaply. In fact, I liked what you said there about using easy to get, inexpensive materials. For one, it also demystifies it for the kids and staying away from fancy materials. But we're going to model what we've done so far is we've modeled the atmosphere with cardboard box. So the cardboard box acts like an insulation, keeping the heat in. We have a little window, and then we just have a 100-watt bulb with a reflector, and that's our sun source. And we keep it at a very steady distance and angle, all of that. So we have a really nice, consistent energy input. And our theory was, actually our original hypothesis is that the air inside would heat up until the delta T, you know, the difference between the inside and the outside temperature would be such that the heat loss would equal the heat gain, and that it would steady out, so that when we run the experiment, it would be a very fast slope upwards, and then it would slow down until it would just steady off and show a steady state temperature. And at that point, you know, it's a dynamic equilibrium. That worked very nicely.
Great.
And then what we then plan to do is then to add insulation, because that's basically like adding CO2 or other greenhouse gases like methane. And we're doing that by just adding more cardboard. And indeed, we then got a second rise, which then came to another steady state. But what we really wanted to show, one of the main purposes, is that we wanted to show what the factors of the thermal equilibrium, the terrestrial and marine. So we put in a tray of rocks in a second experiment, with also some bottles of water for the marine environment, because one of the big concerns for global warming is that not only will the CO2 stay around for a long time if we stop pumping it in, but also just the amount of heat that's been absorbed by the land and by especially the ocean is going to actually slow down the warming and slow down the cooling. And so we wanted to model that. And so far, it's working very nicely. We were using very simple thermometers, just indoor-outdoor thermometers that you get in a hardware store for remote sensing. So far, it's working really nicely, and we're going to continue, hopefully over Christmas break, to continue developing the experiment for the science fair. I just wonder if you had any suggestions on what we might be able to include more that would really model the real weather system even better.
I wonder how complicated you want to make your model, but you could put some water in there. If you could make the model airtight, you might put some ice in there that would melt and then turn to a gas and then maybe condense on the walls of the thing. I'm not sure what that would introduce, but that would take you another step toward replicating the actual planetary behavior. But it would get more and more complicated, and then who knows what noise may be introduced. And one thing I've always thought of with regard to the heat balance of the planet as a whole, and this is a very simple example, but is the bathtub example, is the temperature of the planet is related to the incoming radiation from the sun, and then we leak out heat to space. And it's almost like having a bathtub and you turn on the tap and that's the sun coming in. Then you have a drain at the bottom, and so water is draining away. And it's the competition between the sun's, the faucet and the drain. And if those two aren't in the right balance, the level in the tub will go up or down. And that could be a metaphor or a proxy for the planet's temperature. But that's a very simple example. What you're doing is so much more directly analogous. And I think that's a great project. I bet that'd be a great science fair project. Well, in regard to doing experiments where maybe different groups of kids all had their own boxes, to use your example there, if they each had their own, and they all had their own thermometers, then you get into the issue of not every thermometer is going to be the same. In fact, if you had 10 different thermometers and you hung them from a clothesline in the middle of the same room, they would not all read exactly the same. And so that gets into the idea of noise in your data, and we can only be so precise. And that's something that needs to be controlled as much as possible in any experiment. And I know with the GI Science and Math Enrichment Program here at the university, we've done an experiment where the kids have a whole table full of thermometers. And the thermometers are they're not the most precise thermometers that have ever been produced. And they're like 5 or 10 degrees off from thermometer to thermometer. And whenever I try to work with those kids on that, we try to emphasize the changes in the thermometer from where you started to where you are now, as opposed to the absolute value of the temperature, because otherwise they all get hung up on, well, is it 72 degrees in the room or 75, and everyone's different. And so instrument noise is always an issue too, especially, it's amazing all the noise that's in the data. And well, even the official Weather Service temperature gear, at the Fairbanks International Airport, the thermometer sensor is documented to have, I think it's 1.1 degree Fahrenheit of noise in the temperature sensor. I mean, that's high money gear, and that's, you can't even tell. It was within a degree. It's kind of noisy. You'd think we'd get more precise than that, and it's always good to know the limitations of the data set there, but that can be a little disheartening too. You don't want to put too much confidence in the fine details of your results, and it can hinder duplicatability from student to student. If they've all got their different thermometers, they might have different results that are not due to flaws in what they've done. It might just be the instruments are a little noisy.
Yeah, we're very much in tune here. One of the things that we did was we used 3 thermometers for our experiments, and it was fun the way we did it in class too, because we had to have everybody recording the data and timekeepers and all of that. But we were also taking from different parts of the box as well as to compare, and kind of brought in that issue. You might be curious to know, this is a related issue. Leif Spector at Yale University, he's actually a friend of mine. Just about, I think it's a year or two, maybe even 2 years ago now, he actually invented the world's most accurate thermometer. It was written up in Nature and in Science and many other journals. In fact, his mother, who's a dear friend of mine, has articles from all over the world about his thermometer now on her refrigerator. But he actually uses basic quantum principles. It needs no calibration. It's the first thermometer that really actually is based on physical principles to the exclusion of that problem with the data collection. But anyway, that being said, of course, we're not going to use those kinds of thermometers. But I think what you say is so important. What we saw too with our data manipulation, with our graphing, I wish I had brought them with me. We have huge graphs that the kids made. They're the most incredibly smooth curves I've seen. And I actually was a research scientist, and I know how much the noise typically looks. But these are just beautifully, perfect curves. They're really. Yeah, I was really quite impressed with these. Just Radio Shack indoor-outdoor thermometers. We're going to now use some Mindstorms. We ordered some very expensive. They were $100 thermometers for Mindstorms to go interface with Mindstorms robotics, but they were DCP. They were real professional level, but they were stolen, so we can't use those anymore. So we had to order some lesser ones. But yeah, and working with the kids on the what's equipment all about, and what's the statistical significance of the data. not using that term usually, but I think I agree with you, is a really important part. I have another related question. This is something I really don't understand and I would like to be able to explain to the kids better. Do you understand exactly how the CO2 actually helps retain the heat? Does it absorb heat and re-radiate it back out, and so it goes in 360 degrees so that some of it's going to space and some back to Earth? Or I was wondering if you knew about that.
Sure, Bob. I can talk a little bit about that. I would also, maybe first we should answer a question that came in on Skype from another school. Right? Yeah, and this is a question about your experiment with the box and the simulation of the building the temperature up to the point of a new equilibrium there. Did you have any fans within your box to circulate the air within the box, or was there any exchange from the box to the atmosphere outside the box? So I guess that's a two-part question there. You said there were different temperatures within different parts of the box, so you were not actively circulating the air, or were you?
No, actually, that's a great question. First of all, we had it airtight, so we weren't having any air exchange. I'm sure there was some. I should say that this project came out of actually a course that I wrote and published back in '84, in which we actually have a model house. In fact, I have one in my room here. And it was for teaching kids about insulation, what R value is. Yeah. And we actually mimicked a real house. And for that, I have a fan, because we needed an exactly the same temperature throughout the house so that we can actually really get real accurate measurements of R value. But I wanted specifically not to do that with this project because I wanted it to mimic. So when I said 3 thermometers, we do take at the bottom, the middle, and the top. And then with the thermal mass, we haven't done this yet. We're also going to actually put thermometers into the thermal mass, both the marine and the rocks. But in this case, it mimics the Earth a whole lot better to let normal convective currents to work. And putting a fan in actually would make it less of a mimic of the real system.
Well, with regard to carbon dioxide, I guess the one factor that makes carbon dioxide such a problem with regard to the greenhouse effect is that the radiation coming into the Earth from the sun is a shortwave radiation, and shortwave radiation is not affected by carbon dioxide at all. The carbon dioxide lets the shortwave radiation go right through it down to the planet, and then the sunlight hits the planet and is absorbed by the Earth, and then the Earth re-radiates at its temperature, the temperature of the Earth, re-radiates long-wave radiation, and the long-wave radiation then bleeds off into space. But carbon dioxide is opaque with regard to long-wave radiation. So it's as if the carbon dioxide is just a one-way valve with regard to this energy, because it comes in as short-wave energy and it goes through the carbon dioxide then. But then when it's converted into long-wave energy, it can't escape outward. And that's how a greenhouse gas works, and that's how a greenhouse works. The glass will let short-wave light in, but then the long-wave infrared energy can't escape as efficiently. So you have a net buildup of heat inside the greenhouse. So carbon dioxide, as far as I understand, works in that same way.
Reporting data. So we're going to sign off for now. Thanks again for all your participation, and we'll sign off for today. Thank you.
Bye-bye.